Hello and welcome to Aditya classes, where today we'll talk about dual simplex method. Now, when we look at the name, it says dual simplex method. Now, there is a high likelihood that we might get confused with dual method of solving a linear problem. So, these are two different things: dual method of solving a linear problem, whereas dual simplex method. We have talked about dual method of solving a linear problem in previous lectures. What dual method does is it changes the perspective. It changes the perspective from producing something to maybe supplying something. From a producer's perspective to a supplier's perspective, from a raw material supplier's perspective. I am producing my goods, selling in the market, but the perspective shifts. What if I were the supplier of the raw material? So that is a difference in, that is the idea behind dual, when we solve a simplex problem using a dual method. This is dual simplex method. Now this is different from that dual. That dual is different in the sense that it is a separate formulation itself. First we study dual formulation of a simplex linear problem, and then we solve it using simplex. So that is not dual simplex, rather it is a dual formulation of the problem. I have a problem, I formulate it in a dual fashion. I change the perspective, I shift the perspective and formulate it in somebody else's perspective. That is the dual formulation. If it is my gain, it will be somebody else's loss. If it is my loss, it will be somebody else's gain. So I am shifting the perspective. So that is dual formulation, and then we go ahead and solve it using normal simplex procedure. The normal simplex algorithm is followed. For example, we pick the most positive in net evaluation row, that is Cj minus Zj for maximization, and then we pick the least positive from theta column. So that ratio column, that last one we have. So the exact simplex algorithm is followed in solving a dual formulation also. That is a formulation. That is not a procedure, that is not an algorithm. It is only a formulation, a different formulation for the same given problem. So we should not confuse dual formulation and then the solution through simplex with dual simplex. Dual simplex is something else. Dual simplex is an algorithm, an alteration in simplex algorithm. It is an alteration in simplex algorithm to combat situations where the solution is optimal. Solution is optimal, but not feasible. Dual simplex is an alteration to simplex method. Now understand, dual formulation was an alteration to simplex formulation, linear problem formulation. We had a primal, we had a dual formulation. So that was a difference in formulation, but the solution was coming through simplex algorithm. Exact same procedure was being followed in solving a primal also and in solving a dual also. Here we have a new simplex method, an alternative simplex method, an altered simplex method, which is called dual simplex method. And this method is specifically used where the solution is optimal. Solution is optimal means that net evaluation row for a maximization problem is negative or 0, NER, Cj minus Zj. That is either 0 or negative, hence it is optimal. But it is not feasible. Why is it not feasible? We have a physical constraint, non-negativity constraint. If it so happens that your variables in basis are having a negative value, what do we mean by this? Suppose you have x1, x2, s2, and let us call it s3. Here you have Cj minus Zj, x1, x2, x3, s1, s2, s3. This is minus 4, this is minus x1. It will be a 0, 0, minus 5, let's say minus 2, minus 3 and 0. So if we have a look at this scenario where we have x1, x2 and x3 as our basic variables, we have all negative Cj minus Zj's. Let me put it over here, Cj minus Zj. My net evaluation row, this is my net evaluation row. Now, net evaluation row is either 0 or negative, thereby indicating that the solution is optimal. But when I check values of these variables in basis, what I see is now this is not possible. My simplex suggests that x1, x2, x3, all my variables that I am dealing with should be positive, 0 or positive. At least they should be 0 and preferably they should be positive. But in this case, I am giving a solution that x1 is 8, very good, it is positive, but x2 is minus 2. If your table ends up in this shape, then your simplex has given you a erroneous solution. In such cases, what we do is we move to dual simplex. This is a situation where dual simplex will save us. Dual simplex will take us through this situation. This is a special situation where I have reached the optimal solution, but it is not feasible because x2 cannot be minus 2. For feasibility, x2 should have been greater than 0. In this case, x2 is less than 0. So this is a problem. This is where we make use of dual simplex. So I hope this clears the doubt that what is dual that we have studied up till this point and what is this dual simplex. Dual formulation is completely different from dual simplex. Dual formulation is only a different perspective of looking at the problem, different perspective of formulating the problem, but it is solved through same simplex method. Whereas in dual simplex, we will be having certain different rules. If we end up in a situation like this, we will have some other rules to break this situation. So let us start with our dual simplex method. We have a very simple problem over here. In order to understand, I have taken a very small problem with minimum possible constraints. So let us have a look at this problem. What does this problem say? It says Zmax is equal to minus 2x1 minus x3 subject to x1 plus x2 minus 2x3 is greater than 5. Then we have another constraint greater than 8. Then all variables should be greater than 0. So this is the situation that we have been provided with. So let me convert it. How do we convert it? I multiply this complete problem to minus 1, making it minus x1 minus x2 plus 2x3 less than equal to, because this sign also gets multiplied by minus 1, so it becomes less than, then I have a minus 5. For second constraint, I get minus x1 plus 2x2 minus 4x3 less than equal to minus 8. So these will be my two constraints. As far as objective function is concerned, it is maximization, so no issues. Zmax is equal to minus 2x1 minus x3. We are not touching this constraint because it is as it is in maximization state. Then we have x1, x2, x3 should be greater than equal to 0. So I have changed my formulation a little bit. I have prepared my formulation for my dual simplex method. Now let me go ahead and solve it in routine way. What I will be doing is, this is less than, so I will be adding slack variables. So it becomes minus x1 minus x2 plus 2x3 plus s1 less than equal to, sorry, we have added a slack variable. This side was less than, so I will add something. I have added s is equal to minus 5. Then here we have minus x1 plus 2x2 minus 4x3, another slack, because this is less than, it is falling short, so I will add something, is equal to minus 8. So these are my constraints. I am converting my canonical form into standard form. I also need to add all these variables into Zmax. So it will become Zmax is equal to minus 2x1 minus x3 plus 0 s1 plus 0 s2. So my canonical has been converted into standard. This was the original question. This is question, or rather let us call it formulation. Formulation for dual simplex, and this is standard form of dual simplex formulation. So this is the scenario. Now I have my dual simplex standard form. Can we have our IBFS? IBFS would be S1 is equal to -5, S2 is equal to -8. Now look very carefully. S1 is equal to -5, S2 is equal to -8. If it were simplex algorithm, first condition for starting simplex problem is that IBFS can never be negative if it were simplex algorithm. But here, because we are studying dual simplex, put the name over here. Today we are studying dual simplex. Because we are studying dual simplex method, you can have an IBFS, you can have a starting point as negative value also. So what will be the difference when we go ahead and solve it? Let us go ahead and solve it in normal simplex way. All the row transformations, transferring of your key row, transferring of other rows, exact same simplex procedure will be adopted. The only difference being selection of the incoming variable and outgoing variable. Those will be the two differences. Otherwise, everything will be same. The only difference between simplex and dual simplex would be selection of incoming and outgoing variable. So when we reach there to the selection of incoming and outgoing variable, we will talk about it. For now, let us go ahead and solve it normally. We have our B, we have our ratio. To decide outgoing variables, we have x1, x2, x3, s1 and x1, x2, x3, s1 and s2. So we have s2, s1, x3, x2, x1. Contributions of these are -2, 0. We get contributions from objective function. X is contributing -2, x2 is contributing 0, then x3 is contributing -1, 0 and 0. What is my IBFS? S1 is equal to -5. S1 is equal to -5. These are contributions. Then another one is S2 is equal to -8. S2 is equal to -8. Where are we getting this S1 is equal to -5? We are getting from first constraint. We have a -1, -1 and +2. -1, -1 and +2. Then there is a 1 and 0. Second is coming from this one. -1, 2, -4, 0 and 1. S1 and S2 are contributing 0 and 0. This is our initial simplex table. It is same in dual simplex also. Let us find out ZJs. Again, it is same procedure. Sum product of respective row elements and contributions. -1 into 0, -1 into 0. So it will be a 0. All these will be multiplied to 0. All these will be multiplied to 0. So ultimately I will be getting a 0 in every step. We have 0. Next, because it is maximization problem, I'll go for Cj minus Zj. Cj minus Zj. Right? Cj minus Zj. I'll get a minus 2, 0, minus 1, 0 and 0. If we have a look at my net evaluation row, that is Cj minus Zj, we see that all the values are either 0 or negative. Hence, I can say that the solution that I have arrived at is optimal, because my simplex algorithm suggests so, that if everything is in net evaluation row is 0 or negative, then your solution is optimal. But if I have a look at these B values, these suggest that solution is not feasible. Why is it not feasible? Because everything in my solution should be positive. I am giving a negative solution. So that is not permitted. If we end up in such a situation, then we go for dual simplex. Now, how is dual simplex algorithm different from normal simplex algorithm? As we talked, it is different only in selection of incoming and outgoing variables. Other than incoming and outgoing variables, all same calculations are performed for transferring one equation or one table to another table. Exact same calculations are performed. But yes, incoming and outgoing variables are decided differently. If we rewind back to our simplex algorithm, first we decide upon our incoming variable. What will be my incoming variable? I decide according to the most positive value. So that becomes my incoming variable. Suppose this was a positive value, then x1 becomes my incoming variable. How is outgoing variable decided? Outgoing variable is decided from theta. What is theta? Theta is b divided by my key column. So first I would decide my incoming variable or key column, and then through theta I'll decide key row. But in case of dual simplex, why are we making use of dual simplex? Because the NER, net evaluation row, suggests that this is optimum, but B suggests that this is not feasible. So what I'll do is, I'll switch to dual simplex. And what is the method of selecting incoming and outgoing variables? In simplex, first we decide upon incoming variable, then divide B by respective column to get theta. That theta tells me outgoing variable. Here it is reverse. First I'll decide upon my outgoing variable. Outgoing variable. First we will be deciding on this. How is outgoing variable decided? Most negative. Most negative, B will be giving me my outgoing variable. So I'll not be needing my theta value in simplex. This is the first difference, that instead of first deciding incoming variable and then using theta for outgoing variable, we are selecting our outgoing variable directly from here. It is most negative one. If it happens to be like this, you have some question where your B is 4, 2, minus 3 and minus 5. So these two are out of question because these two are already positive. We are talking about these two, and of these two, most negative is minus 5. This is how we decide upon outgoing variable. So who will be outgoing variable in this case? In this case, my outgoing variable would be S2, most negative. First we decide upon outgoing variable, which is most negative, and then we decide upon incoming variable. How is incoming variable decided upon? Minimum from Cj minus Zj divided by Aj. Cj minus Zj divided by A. These are Aij values. So I have my outgoing variable, so these will be my effective A values. So Cj minus Zj divided by respective A. Cj minus Zj divided by respective A. Cj minus Zj divided by respective A. So let us find out these values. minimum from these values. So ratio would be ratio Cj minus Zj upon Aj would be Cj minus Zj upon Aj. Minus 2 upon minus 1 giving me a 1. Minus 1 upon minus 4 giving me a 1 by 4. Remaining would be 0 divided by 2 would be a 0. So all I need is this value and this value. Minimum from these ratios. Minimum from these ratios is this one. So I have my key row. Once I have my key row, I have my key column. I already have my key column. In simplex, first we got key row, then we used to get key column. This time we, oh sorry, I'm writing it opposite. This will be key column. This will be key row. In simplex, first we used to get key column and then we used to select key row. This time we are first getting key row and then we are selecting our key column. The procedure is outgoing variable is decided from most negative b. Incoming variable is decided by minimum of Cj minus Zj upon Aj. This is minimum. So let us transfer these values to our new simplex table. Our new simplex table would be x1, x2, x3, s1, s2, b with respective contributions of -2, 0, -1, 0, 0. s2 is being replaced by x3. s1 is here only, but we will be having x3 this time round. s1 is contributing 0, x3 is contributing -1. And next, let us transfer these rows. So this is key row. Key row will be transferred here, dividing it by key element. This is key element. We'll divide all elements by key element, getting 1 by 4. This becomes 1 by 4. This becomes minus half. Then we have a 1, 0, minus 1 by 4. Minus half, 0, and this will become minus 8 by minus 4, making it 2. So this becomes my transfer of key row. Next, let us transfer the first row also. What is the formula? It goes like this. Old row minus key column element I multiplied by modified key row is equal to new row. Old row is -1, -1, 2, 1, 0 and -5 minus key column element I. We have key column element I is 2 multiplied by modified key row. This is our modified key row. Minus half would make it plus half in this way, then we have a 0, then this minus would come here and we'll have a 4, then finally we'll have a 2, giving me values of -1, -2 by 4, -4 and 2, -6 by 4. This will be a -2, this is -1 plus 1, making it a 0. This is 2 minus 2, making it a 0. This is 1. This is 1 by 2. This is 5, -5 minus 4, making it a -9. So we get -6 by 4, 0, 0, 1, 1 by 2 and -9. Now making use of our dual simplex method, what we have done is we have converted at least one of the negative basic variables. one of the negative basic variables into positive. Earlier both were negative, now at least one of them is positive. Let me calculate Zj. We have our Cj, let us have our Zj. Then we can have Cj minus Zj. Now these all will be multiplied to 0 at some point of time, so we can leave them. This will be minus 1 by 4. And this is, okay, so this will be minus 1 by 4. This will be half 1, minus 1 by 4, half, minus 1, this will be a 0, this will be a 1 by 4. So we have our Zj's. Then we need Cj minus Zj. Minus 2 minus 1 by 4. So it will be a minus 8 plus 1, making it minus 7 by 4. This will be 0 minus half. So this is the situation. We have our Cj minus Zj. Again, Cj minus Zj's indicate that everything is either 0 or negative, hence it is optimum. But there is a negative solution, hence it is infeasible, hence it is not feasible. So we need to again proceed to dual simplex. What is dual simplex? Outgoing variable, most negative is only this. So I have my key row, I have my outgoing variable. Now I need to decide upon key column. How do we decide upon incoming variable or key column? Minimum of Cj minus Zj upon Aj. So this is my key row this time. So minus 7 by 4 divided by minus 6 by 4, making it minus 7 by 6, or rather minus gets cancelled. This will be our ratio. Then we have, you can leave this, you can leave this, you can leave this, you can leave this. This will still remain negative. This will be minus 1 by 4 divided by 1 by 2. Minus 1 by 4 divided by 1 by 2. Minus half. I need to select minimum from Cj minus Zj upon Aj. This is the selected value. This becomes my key column. Minimum positive. This is my minimum positive. So we have our key column, we have our key row, this becomes our key element. Can we go ahead and prepare our next table and go for further solution? Let us prepare our table over here. x1, x2, x3, s1, s2 and b. Incoming variable is x1, outgoing variable is s1. So I'll be having an x1 and this is intact x3. It is contributing minus 2 and minus 1, so there will be a contribution of minus 2 and minus 1. Minus 2, minus 1, 0, 0, 0. So we have our contributions and everything is over here. We need to divide this complete key row by key element, giving me 1, 0, 0, minus 4 by 6, or I could write minus 2 by 3. And last one would be a half divided by 6 by 4, making it 2, 3. Minus 1 by 3. Last one would be minus 9 divided by 6 by 4. 6 by 4. Negative, negative cancel. 3 2s are 6, 3 3s are 9. 6. We get a 6. So this is our key row transformed. Next, let us go ahead and transfer this second row also. transfer would be 1 by 4 minus 1 by 2, 1, 0, minus 1 by 4 and 2. And then we have minus, what is the formula? Old row minus key column element I multiplied by modified key row, key column element I. This is key column second row, so second element 1 by 4. Key column element I, we are transferring second row 1 by 4, 1 minus 1 by 2 and so on. So it will be 1 by 4, 1 by 4, 1 by 4 and 1 by 4. Modified key row multiplied by modified key row. Here we have our modified key row. We have a 1 double 0, 1 double 0. Then there is a minus 2 by 3. So this minus comes here 2 by 3. Then again a minus by 3. Then there is a 6. We can solve it. 1 by 4 minus 1 by 4 would be a 0. This will be a minus half. This will be a 1. Here we will be having a 2 by 12, making it a 1 by 6. With minus 3 plus 1, minus 2 by 12. Here we will be having an 8 minus 6. 8 minus 6 would be 2 by 4. So our values are 0, minus 1 by 2, 1, 1 by 6, minus 2 by 12 and 2 by 4 or 1 by 2. This is our Cj, then we can have our Zj's. This will be a minus 2, this will be a half, this will be another minus 1. We have a 4 by 3 or rather 8 by 6, 8 minus 1 is 7 by 6. Then we have a 2 by 3, then there is a 2 by 12. 2 by 3 can become an 8 by 12. 8 into 10 by 12. We can have our Cj minus Zj. Minus 2 is 0, negative half, 0, negative 7 by 6, negative 10 by 12. Now again everything is negative or 0, hence it is optimum and also it is feasible. So can we write that solution to my dual simplex is solution to my dual simplex is x1 is equal to 6, x2 is equal to 0.5. And for x1 is equal to 6 and x2 is equal to 0.5, you could have your Zmax. Zmax is equal to minus 2 multiplied by x1 minus x3, making it minus 2 multiplied by 6 minus, sorry, it is not x2, it is x3, 0.5, making it minus 12 minus 0.5 or minus 12.5. So this is my final solution using dual simplex. Now I have a solution which is optimal also and feasible also. The only difference between simplex and dual simplex is, in simplex first we decided the incoming variable and then we used to divide b by the incoming column to get theta, and that theta would tell me the outgoing variable. So incoming variable was somehow leading to outgoing variable. In this case, dual simplex, we first decided the outgoing variable. How is outgoing variable decided? The most negative b. This outgoing variable tells me my incoming variable. How? Minimum positive from Cj minus Zj upon Aj. This is Cj minus Zj respectively upon Aj. I am interested mainly only in positives and then from them also minimum positive. So this is how we select. Fine. So this is our dual simplex method. Next time when we meet, we'll take up one more problem of dual simplex so that we can get accustomed to simplex. Yes, today we took a maximization problem. Next time we'll take a minimization problem to see what is the difference. If you remember, in simplex there was only one difference between maximization and minimization. That difference was, instead of taking Cj minus Zj, we take Zj minus Cj. That is the only difference. Instead of Cj minus Zj, go for Zj minus Cj. In this case, dual simplex, when we meet next time, we'll take up a Zmin problem and see what is the difference. Until we meet next time, do take care. Thanks for watching. Bye-bye.